let's start the lecture 9. First, let's recap what we learned last week. We learned single sideband last week, right? And the basic of single sideband is that simply you can compare the double sideband with single sideband, right? This is a double sideband. As you can see here in the pass band here with the center frequency of the carrier frequency, you see that the left side and right side, or you can say the lower or upper sidebands, both looks same, right, in general. So this was a double sideband, which means that since both things have the same information, it's like you have here on the left and right, but it's kind of duplicate somehow. But you can use this way because you can simply make this DSB signal by multiplying message with the carrier. Okay, then you can make this kind of spectrum and transmit in the air. But in single sideband, what you can do is you can take only the upper sideband like this, or you can take only lower sideband. The main reason is you want to use a spectrum much more efficient, right? Much more efficiently, right? So in this case, you need a bandwidth of 2W. Your original signal looks like this, right? Original signal in baseband looks like this. When you multiply the cosine carrier, now the frequency is modulated, right? It's shifted into the center frequency of FC. So now you still have you're going to have a bandwidth of 2W. That's the case of double sideband. But in single sideband, your bandwidth is now half of the bandwidth of double sideband, right? So the advantage of single sideband is you are using only the smaller or narrower bandwidth. But you can still transmit the same information. So we can say it's much more efficient because you use only small amount of spectrum. Okay, that's the main reason. But in order to make this single sideband, at the transmitter, you need to do more calculation, right? It's going to be a little bit more complex. Earlier in the DSB, as I said, what you need to do is simply multiply message with the carrier. Okay, MT times CT, like MT times CT, right? Simply, that's what you need to do in the double sideband. But in single sideband, it's going to be a little bit more complex. And simply speaking, how you can do is this way. Look at the equation on the bottom of the slide here. So this is a upper sideband, upper single sideband signal. So this is what you transmit over the air, right? And you can see that there are two terms. And the first term here, this one, is actually same as a double sideband, right? But you have one more term in single sideband. And in order to create this second term, now what you need to do is you need to do Hilbert transform. Okay? So simply speaking, in the double sideband, you can simply create your double sideband signal by multiplying MT-CT. Okay? That's what you need in the double sideband. But in single sideband, you have to do this way because the first term is the same as the double sideband. But in addition to that, you need to also have this second term. And this second term needs to be calculated by Hilbert transform. So you need to have a Hilbert transform at the transmitter. Okay? Right? And remember the Hilbert transform? So this was a Hilbert transform. Right? So Hilbert transform is nothing but just a filter. But this is an all-pass filter, meaning that this filter does not change anything of your magnitude or amplitude. Right? Whatever signal you have, your output has same magnitude. So magnitude does not change. But what you change, what's going to be changed is the phase. Okay? As you can see here, if the XF, let's say, is a frequency response of your input signal, now the X hat F is the frequency response of your output signal. And the output signal looks like this, right? If the frequency is a positive, now you have a minus 90-degree phase rotation. negative frequency, it's 90 degree phase rotation, right? So that's what it is. So depending on the positive or negative frequency, now your XF is rotating minus 90 degree or plus 90 degree. Okay? That's what happened in the Hilbert transform. Okay? So mathematically, the Hilbert transform in frequency response of this Hilbert transformer is minus j signum function. So signum function is defined this one. So that's your transfer function of your filter or Hilbert transform. So simply speaking, right, you can remember this picture. Okay, remember that the 3 dimension that I was talking about is just to help you to understand, right? There's no 3 dimension in reality. Okay, there's nothing in 3 dimension in real. But what I'm talking about 3 dimensional is to help you to understand. Okay? Okay. So as you can see here, you can see this is a frequency. X axis is a frequency, and y axis is your frequency response. And we can virtually make another axis which indicates a phase, right? And as you can see here, original spectrum looks like this. Original frequency response looks like this, right? But as you can see here, in the positive frequency, you have a minus j, minus 90 degree rotation, phase rotation, and negative frequency, 90 degree phase rotation. So positive, negative now is rotating in different direction, right? Positive frequency, minus 90 degree. Okay? Negative frequency, positive 90 degree. Okay? That's why now the positive spectrum, positive frequency response, negative frequency response is now splitted. Earlier it was all together, right, with the phase 0, but now it's splitted. One goes to positive 90 degree, negative 90 degree. The other one goes to positive 90 degree. So we are separating here, right? All these things is done by Hilbert transformer. As an example, now you can see that when you put the cosine, simple cosine, put the cosine into the Hilbert transformer, now you're going to get sine. So we learned that sine actually looks like this, right? We know that cosine always looks like positive frequency, negative frequency like this. But some of you probably remember the sine is like this, right? But that's not. It is actually, there is a 90 degree phase rotation. How do you know? How do you know? You know Euler equation, Euler identity, right? That means exponential, let's say exponential ix equals to cosine x plus j, let's say j sine x. Is that correct? Yeah. Then in the same way, using the same Euler identity, what you can write is the cosine is actually half of e jx plus e minus jx, right? That's a cosine. And what we are talking about here is 2 pi fct, not x. So you can put that 2 pi fct here. Then 2 pi fct plus minus. So when you look at this, right, cosine is actually same as half times exponential with another exponential, but this exponential has the exponential power exponent of fc. This one has minus fc, right? So that's why you see this one, which is positive exponential. This one is a negative exponential, right? Same way, What is the sign? Sine equals to what? Does anyone remember? To J. Here's a J, right? There's a J here. And then you can see that something like this, right? So now you have one positive and one negative. That's why some of you remember positive, negative, like this for sine. But what you forget is this one. There's a J right here, right? There's a J. So when you put the J on the denominator here on the bottom, what you can do is, J, 1 over J equals minus J, right? It's same as minus J. So now I can change this into minus J. Then you can see that this is minus J, so minus 90 degree. So for this guy, minus 90 degree. That guy, you have a minus J, minus, so it's going to be plus, right? So this guy, we have a J. So there is actually J, or minus J. So that's why it's not like this. It is like this, right? That's why you see there's a minus 90 degree phase rotation and 90 degree phase rotation here. Okay, so that's why I'm saying this is a more accurate way of looking at the sign. Okay. But anyway, coming back to Hilbert transformer, so put this one into the Hilbert transformer. Now you're gonna get this, right? Yeah. Now you're gonna get this. Now when you look at the upper sideband, again, and as we discussed, the first term is a double sideband, and the second term is a little bit complex, but in the second term we have the Hilbert transformer output of your original message. So putting MT into the Hilbert transformer, now you're going to get M hat T. But in fact the MT let's say was like this, then we know that M hat T has a spectrum or frequency response like this, right? So that's M hat T, and you multiply sine. So original one here, DSP, you multiply with the cosine carrier, but our Hilbert transform output of your message, you multiply the sine carrier. Okay? So intention is that by doing this, you have two terms in upper sideband. In the first term, we originally have a double sideband, so the frequency response looks like this. So that's a double sideband. And in the second term, we are going to create this kind of spectrum. That way, when you do minus this one minus this, you're going to get this, right? So that's how you create the upper sideband. Okay? So intention is by doing this Hilbert transformer, now this upper band and lower band, you're going to split, and then doing another phase rotation to create this kind of thing. Now then you're going to this one minus this, then eventually you get this upper sideband. Same way, when you do addition, now you are adding this one plus this. Then of course this lower band, actually upper band, will be cancelled out because here's a positive, here's a negative. So therefore you're going to get this, right? So that's how you create the lower sideband. Okay. So that's everything for a single sideband, pretty much. Here's one simple example. Let's say our original message, MT, has the magnitude frequency response like this. So what you're seeing here is MF magnitude. Okay, this is MF. Earlier in the previous picture, we always assume that our MF looks like triangle, right? But in this case, as an example, we are assuming that our original message has the frequency response like this. This is our original message. Okay, that's our original message. So let's think about that way. if our original message looks like this, like that, right? That's our original message MF. Okay. Now using this original message, what we want to do is we want to create single sideband spectrum. Then first thing to do is you're going to multiply the carrier, cosine carrier, then this one is now frequency shifted. So now you're going to get this spectrum, right? That is going to be your double sideband signal in frequency domain. And also what you need to do is you want to put this one into the Hilbert transform. Now you're going to get H hat, not H, M. M hat F. Right? And what does it look like? If we draw it 3 dimension, it's going to be like that, right? Something like that. And put this one, this is M, the output of Hilbert transformer, M hat T or M hat F, and you're multiplying sine carrier into here. Then eventually, you're going to get this, right? So this one is what I'm showing here is a frequency domain response. But how to create this DSB is in time domain, you are multiplying message with the carrier, right? So that's how you create this signal, but that's frequency domain. Same way, you put this original message into Hilbert transformer, then you're going to get M hat T in time domain, and multiply the sign in that time domain signal. And then looking at the frequency domain, this is the frequency domain response of this signal here, right? Now what you need to do is, if you want to get upper sideband, okay, if you want to get upper sideband, then you need to do minus. This one minus this. Then you're going to get upper sideband. If you want to get lower sideband, then you are going to simply add these two. Then you're going to get lower sideband. Okay? That's how you get. So what you are seeing here is actually upper sideband. You're only looking at the positive frequency. So this one was original baseband, like this, right? And now you create these two, and let's say you do this minus this, then you're going to only have this upper sideband. So that is upper sideband. Okay, there's one more here, but in this picture, it's only showing the positive frequency area. So you see here's FC, right? And we only see the upper sideband. This is a case of lower sideband. Here's FC, and you see only lower. Okay. Same way, if I draw it here, this one minus this, you're going to get this, right? That's what you see right here. Okay? This is this one, upper sideband. Upper single sideband. Okay? That's this one. Okay? Yeah, so our original message is empty, so we're starting from that, put it into Hilbert transformer, we're going to get MT, M hat T, right? That's the output of your Hilbert transform, and then multiply the sign into that, and in original MT, you multiply cosine. That's the same as DSP. So you create the DSP signal, and you are creating this kind of signal, and you do minus. This one minus this. Then you're going to get this upper sideband. That's what you see here. Okay. This picture is from the textbook. Okay. And then what this picture shows is this one. Okay. Okay. What we're going to discuss here in the slide is a little bit more piece of information, like how to create the this single sideband. Okay. So there are two different ways. Actually, this slide shows you first way, and this one, the second slide shows the second way. And this second way, which is called a phase discrimination method, is same as what we discussed. Okay, so we're going to cover that next slide. First of all, we want to talk about frequency discrimination method. Frequency discrimination method. Now let's come back here in this picture. Okay, think about this way. This is our original message. Let's think about very simple. This is our original message, only looking in the frequency domain. And this is the signal we want to transmit over the air. Okay, so forget about all these equations, forget everything. What is the easiest way to do it? Just forget all these things, right? This is our original input, original signal. This is what you want, because this is what you transmit over the air. So what is the easiest way? Easiest way probably is, first you multiply cosine, make this, right? We already learned that, right? That's DSP. You created this one by simply multiplying cosine, and then you can put a bandpass filter. Okay? When you put the bandpass filter like this, then what happens is this band will pass, the other band will be blocked. So you're going to get this, right? So you can simply go through the bandpass filter. That's this one. That's what you're seeing here in the frequency discrimination method. You have original message MT. You multiply the carrier wave. Okay, once you multiply the carrier with the message, what do you get here? Right here, you're going to get the DSP signal, right? Remember, the DSP double sideband signal is simply MT times CT. Okay, so right here at the output of product modulator here, you're going to get DSP signal. So what does the DSP signal look like? Like this, right? That's DSP signal. So that's what you get here. And right after that, simply you can put the bandpass filter. And what kind of filter is that? That bandpass filter has a pass band of this one, and the other frequency you block. Once you do that, right, you can easily get this, right? Yeah, so that's one way to do it. Frequency discrimination method. That's why we call this frequency discrimination. What is a discrimination? Yeah. Yeah, right. So that's a discrimination. So you are discriminating in the frequency domain, right? In the frequency, because you put the filter in the frequency. In the frequency domain, you are basically separating or discriminating these things simply. So that's why we simply call it a frequency discrimination method and using the bandpass filter. But this problem, this method has a little bit problem, right? Ideally speaking, this seems to be the best way, but now the problem is we cannot design the perfect bandpass filter. So always when you design a bandpass filter, not just bandpass filter, any frequency filter, low pass filter, high pass filter, bandpass filter, all the filters, you always have a roll-off region like this, right? You never design like rectangular filter. It's not possible, right? In practice, It's never be possible. So what is mostly happening is you're going to have roll off, like slowly going up, going down. So when you apply this kind of filter here, what is possibly happening is you have a filter like this, filter like this. So if your filter response looks like this, right, then you're going to have some error here. You will have some unintended signal right here. So we don't want that. So that's why this method may not be accurate. Looks like simple, but that's not very good, right? So better way would be this one, phase discrimination method. Okay, that's a second method. And how to do that in this phase discrimination method is exactly the same as what we discussed earlier using Hilbert transformer. So in this method, we have an empty original message and put it into the wideband phase shifter, but this wideband phase shifter is same as Hilbert transformer. You get output M hat T right here, right? So this is same as Hilbert transformer. So putting into the message into the Hilbert transformer, now you'll get M hat T. Original message, in the meantime, you multiply into cosine carrier. Output of the Hilbert transformer, you are multiplying sine. And then you either plus or minus. So that's exactly, this block diagram is exactly same as what we discussed for single sideband creation. Okay? Right? That's exactly the same, right? When you multiply original message into carrier, now you're going to get DSB signal here. Put the original message into Hilbert transformer, now you get M hat T, multiply sine, then now you're going to get this signal right here, right? So that's the signal you had here. Here you get this signal. And up here you're going to get the DSB. So when you look at here, if you do minus, then you're going to get upper sideband. When you do plus, lower sideband, right? That's the output. So we call this one as a phase discrimination because you are changing the phase, right? You are discriminating phase. So that's why we call that phase discrimination method. Going back further, we already discussed the frequency discrimination method. In this case, no Hilbert transform, right? We don't care. Hilbert transform, phase rotation, whatever. We don't care. What we do is simply using the bandpass filter, we are just separating. We are just simply discriminating in the frequency domain. That's what you have here. Looks like simple. It is actually simple, but this filter is not ideal. So the signal may not be perfect. So that's a problem. But in phase discrimination method, the hardware looks a little bit complex. Right? That's a problem. So far we discussed how we create a single sideband signal. Whenever you see modulators, right? Modulator, that means transmitter, right? At the transmitter, you are doing modulation. At the receiver, you are doing demodulation. Right? So every time you see the modulator, that means transmitter. So we are still talking about transmitter. At the transmitter, you are doing all this. At the transmitter, you start from original message and doing all this, and you create the single sideband spectrum, single sideband signal ST. Now ST goes over there. Okay? Still, we are talking about transmitter. Okay. Now then, how do you receive? We need to talk about how to receive and how to recover the message. Okay? To discuss the receiver, I'd like to remind you the receiver of DSB. First, let's look at receiver of DSB, first of all. And what's the name of the receiver of DSB? We discussed two things, right? Coherent detector. And second thing is Costas receiver, right? So let's first discuss the coherent detector. And how to do that in coherent detector is you receive some signal. So I call that RT because we are talking about receiver side, right? The input is RT, but this RT is actually same as transmit signal. Transmitter generate the signal ST and transmit, right? And then receiver receive it, right? So from the receiver point of view is RT, but actually RT is same as ST because we have no error. Whatever you transmit, it's exactly same as whatever you receive, right? That's our assumption here. So we are going to get ST at the receiver. And what you do is you are multiplying carrier, cosine carrier. And your carrier at the receiver may have a phase mismatch. And then what do? You need to put filter. That's it, right? That's the receiver. And this receiver is called coherent detector, right? And our original ST looks like MT times cosine. I'm still talking about DSP, okay? Just reviewing the DSP. And now let's assume that phi equal to 0. Just assume that phi equal to 0. So there's no phase mismatch. Phase is exactly aligned. In that case, right here, we call that as a VT. And now we know that VT looks like MT times cosine square 2 pi FCT, right? And you know that cosine square x equals to half plus cosine 2x, right? You know that. Based on this identity, now you want to change this into MT times half 1 plus cosine 2 pi 2FCT. That's what you have here in the VT. Now you want to put this VT signal into the low-pass filter. Now when you put this signal into the low-pass filter, what happened? The second term is going to go away because this one is a high-frequency component, and this high-frequency component is blocked by low-pass filter. Only the DC component will pass. So therefore, eventually, you're going to get MT times 1/2, right? Half of MT. That's the output you get here. That was the case of DSP, right? Yeah. Now let's consider the case of SSB. SSB. Okay. Now we want to discuss SSB. In SSB, what is transmitted is DSB signal. Let's think about upper sideband. Actually, lower sideband is same, but let's think about a upper sideband first. In upper sideband, the ST looks like this one minus M hat T sine. Okay, this is your upper sideband signal in time domain, right? That's what is transmitted over the air. So of course, at the receiver, you're going to receive this because this is what is transmitted, right? You have two terms in time domain, right? Let's go all the way back. This is what you are transmitting over the air. So forget about half. This is constant. So for this one, it's not important. And also AC, this is not important, right? So think about only MT cosine and M hat T sine. That's the important thing. Now you have this one as ST. So that's the case of upper sideband. And this is the signal you transmit over the air. That's the time domain signal. And when you look at this one in frequency domain, this is the frequency domain response. So this one and this one is the same thing, right? This is just time domain. that is a frequency domain. So we are transmitting this signal over the air. So from the receiver point of view, we are receiving this signal. Now what you need to do is we want to use the same receiver. This receiver is a coherent detector, right? Let's use the same receiver, same as a DSB. Okay? Put that here. Now what you want to do is, again, at the receiver, you are using cosine carrier. Let's assume phase mismatch is 0. Now then we want to consider the VT here. In the VT, you are multiplying cosine into this. But in our ST now we have two different terms. So when you multiply cosine into the first term, we're going to get the same thing, like this. And the second, when you multiply cosine into the second term, now we are going to get cosine times sine. So that is our VT right here when you use a upper single sideband, right? So this is our VT, right? Yeah. So we're going to still use this identity, and also we want to use another identity. Cosine x sine x equals half sine, maybe you can do it like cosine alpha sine beta equals half sine alpha plus beta. Is it plus or minus? I'm not sure. Probably plus. I'm not sure. Something like that. Okay, I don't remember exactly. This one may be minus. I don't remember exactly, but you can look up. Okay, in high school mathematics. But this is not important for me. But anyway, I'm not sure this is exactly correct. But the idea here is you multiply cosine and sine, then it's going to be sine plus sine. It's basically the same thing as identity. So I want to use these two trigonometric identities. This one, we have cosine, so therefore I can rewrite is this into 1 plus cosine 2 pi 2fct. Okay, I used this first identity here. For the second term, m half t, I want to use a second identity here. In that case, half. When you add these two, it's going to be sine 2 pi 2fct, because it both are same, right? So when you add these two, and when you do minus this one, 0. Right? Both are same anyway, right? So plus 0. That is VT. This one is actually same as this, right? I just simply use an identity. So both are same. Both are same. So that's our VT here. In case of upper sideband. Now what's the next step to do? Put this VT into low pass filter. That's the next thing to do. Okay, let's put this one into low pass filter. Now then, this cosine term is gonna go away, right? Because this one is a high frequency component. So now let's kill this guy. What about this one? This one is also 2FCT. This is also 2FC component, high frequency component, right? So using the same low pass filter, this one and also this one, both one is gonna go away. Both are killed, right? Then what do you get? The output is only this one. Because in the second, in the second term, you only have this term, right? Because this is 0, you only have this. But this one is going to be removed by low pass filter. So this is removed by low pass filter. That is also gone by low pass filter. So you only get this. So what is the message? What I'm talking about here is in the upper single sideband case, the receiver is going to be same as DSP. That's what I'm trying to say, right? Okay? So receiver is the same. DSP receiver, SSB receiver, same. Okay? Simply. That's the message here. Okay? And you can prove that by these all equations like this. It's a very simple way to do it. Okay? You can prove that. So no difference in the receiver. I just talked about the coherent detector here, but for the DSB, you know that there's a costas receiver, right? Then what about the upper sideband? Can you use a costas receiver for the upper single sideband? Of course, right? Of course. Yeah. So for the receiver, it's no difference. Same receiver you can use, same receiver, coherent detector or costas receiver, same receiver you can use it for both DSB and also SSB. Okay? So that's why there's no details here. Okay? There's nothing more to say. I can just say that receiver is the same as before, same as DSB. That's it. Okay? No much difference. And remember that why? That's because you are multiplying sine into the Hilbert transform output, right? You multiply sine. And now when you look at all this equation, now you remember when you multiply sine, eventually going through this way, at the receiver you multiply cosine, then it's going to be like cosine times sine. You multiply sine at the transmitter, and at the receiver you multiply cosine. So eventually you're going to get like cosine times sine. When you see the cosine times sine, it's going to be removed by low pass filter. Okay, so that's what it is. But okay, there's one trick here, right? There's one trick. What is that? This is only true when phi equal to 0. Okay, so let's discuss a little bit more when you have phase is not 0. Let's say phase is not 0. Just to discuss a little bit further. Okay. Okay, if the phase is not 0, we know that what happened, right? This one is a 2 pi FCT by transmitter, and we are multiplying 2 pi FCT plus phi. And this one is from the receiver, right? So you're multiplying two different cosine and with two different frequencies, but we only have a phase mismatch. So this cosine is from the transmitter, the second cosine is from the receiver, but we have phase mismatch. Same thing, we originally have a sine multiplied by transmitter, and you are multiplying cosine in the receiver, but cosine has the phase mismatch. So that's what you have as a VT. So this is your VT. When you have a phase mismatch, like phi, this is going to be your VT, right? This is your VT. And you can still use the same identity. Actually, it's not same. Yeah, not same. It's like, since we are seeing different phase here, cosine times cosine, it's going to be cosine alpha plus beta. Is it plus or minus? I keep forgetting. I think it's plus, right? Yeah. It's a long time since I see these things. So I don't remember exactly. I think this is right. Okay? Yeah. So you see the cosine alpha times cosine beta is addition of two different cosine. So let's do that. You see that you are adding these two. It's like 2 pi 2fct plus phi plus cosine. This one minus this is going to be cosine phi. this is from the first term. Now minus, let's look at the second term. Second term, you can still use these things. Sine 2 pi 2fct plus phi plus sine phi. That's your output, right? That's your VT. When you have a phase mismatch, that's your VT right here. Right? So next thing to do is put this VT into the low pass filter. Then by low pass filter, now this term is gone. This term is also gone. Then your output is MT. This one minus that's your output, right? That's going to be your output when you have a phase mismatch. Yeah. So if you remember DSB case, in double sideband case, if you have a phase mismatch, that was the output. Remember that? This was the output from the DSB when you have a phase mismatch. But in single sideband, you have one more term, like this, sine phi. Because we have a phase mismatch, and you're going to get this term in here. So that's the result. It's easy to do it, right? Very easy to do it. Yeah. Yeah, it's very easy to do it. And I want every one of you to do all these things in the equation. Since this is a pretty simple one, look at this. This is actually a pretty good question. For example, in midterm, right? For example, in midterm, this is very, very nice and clean and easy to do it for a midterm exam. I'm just giving you an example. Okay. Anyway, when you have a phase matched, then you see that the receiver is no difference between the DSB and SSB. So that's the message. We have a new terminology here called the frequency translation. Okay? But this one is, yeah, that's what we talk about here. But this one is not that important. But let me tell you a little bit here. What this frequency translation means is sometimes, right, you want to change the frequency. You have some frequency, let's say F1, and you want to change F1 into F2. Okay, you want to change the frequency, let's say. Then how do you do it? I'll give you an example. Let's say in your cell phone, right? You everyone has a cell phone. In your cell phone, your message or your voice, you originally start from the baseband. Okay? But into the carrier, in order to transmit over there, you need to do modulation and you need to go to the carrier frequency. And the carrier frequency is something like 1.8 gigahertz. But jumping from DC or baseband into the 1.8 gigahertz, that's a big jump, right? So in a lot of cases, what they do is you're going to jump into some frequency in the middle, like some 100 megahertz or something like that. That's we call as a IF. You jump to IF first and then jump. So it's like a second jump. Okay? They typically do that. We call that as a super heterodyne receiver. Heterodyning. Heterodyning means you're jumping not just big jump. You are doing like jump, jump, like 2 times, right? Using the intermediate frequency, IF. That's heterodyning. So there are a lot of cases that you see frequency translation. You are changing the frequency and changing it again, or maybe again, right? You need to change the frequency a lot of times. So how do you change the frequency? I mean, we already discussed many times how to change the frequency. How do you change the frequency? By multiplying cosine. Simply, right? Simply let's go all the way. Our original signal was in the DC, in the baseband. So center frequency was 0, right? But before you transmit, how to do is you now change the frequency, center frequency into FC. So you are basically doing, originally your signal was here, but you are jumping to this, right? So you are simply changing the frequency. That's kind of frequency translation. And how to do that? How to change from this to that? Multiplying carrier. And your carrier has this frequency FC. That's the way, right? Right? Simply multiplying cosine carrier, you can change the frequency. Now then, okay, so let me tell you here. Let's say your signal was originally in baseband, and if you want to change frequency translation into FC, now you're multiplying cosine into here. Then you can simply change it to this. Now then the question. Let's say your signal, original signal was in F1. Okay? In F1. Now you want to change it into F2. F2 is a little bit higher frequency. F1 is somewhere here. And now you want to change it to F2. How do you change it from here to here? From here to here, we know that multiply cosine simply. But here to here, how do you do it? That's what we're looking at here. Okay? But simply speaking, how to do that? When you do translation, frequency translation, how to do that is in hardware, we have a hardware called a mixer. Okay? Maybe you want to remember something like this. Mixer. Later, when you work in your job, you can probably, some of you probably hear mixer a lot of times. Every time the people say mixer in industry, okay? In the company, people call the mixer. That means you are translating the frequency. You are changing the frequency. And what mixer means, mixer means mixing two different things, right? What is mixing? We are mixing frequencies. We are mixing two different frequencies. That's the mixer. So always the mixer has two inputs and one output. Sometimes two output, but typically one. So what you're mixing is you are mixing two different frequencies. Mixing two different frequencies. When you're mixing two different frequencies, what's going to be the output? Generally, right? Generally, when you mix two different, okay? Think about very simple. What I'm talking about here is, as I said, mixer is simply hardware, like this, right? Something. But when I write this one in the mathematics is very simple. Inside here, you are doing multiplication. It's like this. I'm basically mixing two different frequencies, meaning you are basically multiplying two different frequencies. When you multiply two different frequencies, what's going to be the output? When you do this, right? What's the output? It's like you're going to get F1 plus F2 frequency as the output, and also you're going to get, let's say F2 is a little bit higher frequency, then F2 minus F1 as the output. So you're going to get two different outputs, right? When you mix two different frequencies, always the output is going to be F1 plus F2, that's one output. F1 minus F2, that's another output. Okay, you're going to have two outputs. See, like here? What you can see here is the input to the mixer. Okay? And this input has the mixer frequency F1. Now when you put this one into the mixer and you are mixing with another frequency, FL, I think this is FL, right? Yeah. It's not, the picture is not clear, but it's you are basically mixing FL frequency. So your input is F1 frequency, and what is mixing? Second input. Second input has another frequency. It's a little bit hard to see, right? That's FL, I think, FL. So when you're mixing two different frequencies, what happened inside of the mixer? This is a mixer, basically. This is a mixer. Okay, the whole thing is a mixer, hardware. What is inside here is simply you are multiplying two different cosine, like this. Then, since we already know the identity, you want to change this multiplication of two cosine into addition of two cosine. That's what happened here. So the output S prime t looks like this in frequency domain. Okay? So you have F1 plus F2 frequency here. In this case, actually, the second input is FL. So this one is F1 plus FL here, right? So that's F1 plus FL. What about this one? This one is F1 minus FL. So you get these two different output frequency. Why? Because we multiply two different cosine. Cosine F1 times cosine FL. So using that identity, we know that it's actually same as F1 plus F2, F1 plus FL, F1 minus FL, two different frequencies. What is the next thing to do? Next thing to do is you don't want two different frequency outputs. You want only one output, right? Maybe you want this, then you're going to kill this one. Or maybe you want this, then you're going to kill this guy, right? So depending on which one you want to remove the other one. That's done by bandpass filter. So this bandpass filter maybe pass this guy and remove this. Or this bandpass filter is passing this guy and remove this. It depends on the hardware. It depends on the mixer. So that's why sometimes you have one output, but input is two. That's a mixer. Okay, that's a mixer. We discussed this already, right? Yeah, we discussed everything already. But you can see this mixer in hardware, actual hardware. You see these things. So we are using these things in hardware to do the single sideband and also a double sideband. But that's how things work. Okay, that's a frequency translation. And what you look at in the slide is like this, right? When you add these two or minus these two, you're going to get a new frequency. That's what that means. Okay, that's pretty much it for single sideband. Now this is the last different modulation of amplitude modulation. So far we discussed three different amplitude modulations, right? Some basic, like a DC addition amplitude modulation, double sideband, and single sideband. Okay, which one is the best? If you think about spectrum efficiency, single sideband is the best. But receiver simplicity, the basic DC added amplitude is better. Amplitude modulation is the best, okay? But typically single sideband is best, right? A little bit complex, but still it's best because spectrum efficiency is the most important thing. Now this is the fourth one, last thing. We call it as a VSB, vestigial sideband. Okay, that's the last thing. And here's the idea. This, by the way, this vestigial sideband is only used in TV, analog TV. We are not using analog TV anymore, right? There's no analog TV. So this is just history. Like 10 years, 20 years back, 20 years ago, they were using VSB. But no one is using this one anymore, right? We are not using analog TV. We are using digital TV these days. So I don't think this is that important. So we're going to just discuss some of the basic concept of this VSB, and it's not important to talk about the details. And the main intention of this VSB is that when you look at the TV signal, right? TV signal is wideband signal, wideband. Why is that? Because you need to transmit some image, right? Typically image or TV screen, it has a lot of information. So you need to have a high data rate. So your bandwidth is large. So it's a wideband signal. Not only that, when you look at the TV signal, you have image, screen, image signal. You also have voice, okay? Right? Voice signal and also image signal. But typically voice is low frequency. And also image has a wideband. So because of that, this typically the TV signal, it's not very good idea to use a DSP and SSB. Actually, just SSB is not enough for this TV signal because in the TV signal, as we just said, it's a very wideband. Okay, TV signal is typically wideband. Now let's think about using SSB. Once you use SSB for this guy, now it's going to be like this, right? Since you are using only the upper side band, right? You are taking only this guy, and you are going to use upper side band. So this kind of single side band is not good for this kind of wideband signal. So what they do is this is the case of double sideband. This is the case of single sideband, right? So instead of these two, what they are trying to do is they try to use a VSB. And how they do in VSB is that, okay, in this double sideband, you use both sides. In single sideband, you use only one side. That's difference, right? In VSB, how to do that is you are using like 90% of your upper sideband and maybe 10% of single sideband. I mean, in this lower band. So what they do is they use both bands, but most of the signal goes to this, and some signal goes here. That's what they do as a VSB. Okay. Yeah. This case, you use both of them. Same thing, same way as the original spectrum, your baseband signal. But in this case, single sideband case, you only use one side. But in this case, you use most of the signal in the upper band. Lower sideband, still you use it, but a little bit. That's the VSB. So to do that, we need to have the sideband shaping filter. Because how do they do it is, you have original signal here in frequency domain, right? Put this frequency domain into the shaping filter to create this signal. You need to put this guy into the filter. That filter is shaping filter. Put this original spectrum into the filter now to create this as the filter output. So that's the sideband shaping filter. Okay, let me show you how it looks like. Yeah, this picture probably shows you better picture here. See, this is our original signal. Let's say TV signal. This is like wideband TV signal. Now what you want to do is, first you multiply cosine. Okay, when you multiply cosine, it becomes the DSB. Right? So this is original signal, original message, multiplying cosine into this one, then now you're going to get the DSB signal like this. So this is a DSB, original DSB, right? Put this DSB signal into shaping filter like this. This is a filter we are talking about, shaping filter. Put this DSB signal into the filter. Now you're going to get this output. That's the VSB output, vestigial sideband output. So this is what you transmit over the air. Okay, this is the signal you transmit over the air. So when you look at this signal, now you can see that this red part is a little bit changed, right? And also you can still transmit some of the blue part. If this one was a single sideband, then what happened was you're going to transmit only the red one. But that red one has a perfect shape, original shape, right? That's what you transmit in single sideband. But in this case, the vestigial sideband, even red part is a little bit different, and the blue one, you transmit only small part. That's what happened in vestigial sideband. So that's what you transmit over the air. Now let's think about the receiver side. This is what you transmit. Then what happened at the receiver? At the receiver, it's basically doing the same thing. And how to do that is you're multiplying cosine carrier. That's what we did all the time, right? Think about coherent detector at the receiver. First thing to do is multiplying cosine carrier. Maybe you have a little bit of phase mismatch, but still you are multiplying cosine carrier, right? That's always what we do at the receiver. When you multiply cosine carrier, now what happened? Think about it. Now what happened? So this is a VSB signal you transmit over the air, right? This is what you transmit over the air. Now from the receiver point of view, you receive this signal and multiply cosine. Now then what happened? Since you multiply cosine carrier, same carrier, this signal, this spectrum moves to the right, moves to the left, right? Since you multiply cosine. Same thing for this guy. Then now what happened is, this spectrum, this guy moves to the left, right? Because we multiply cosine. So this guy now shows up like this. Same thing from that guy. When we multiply cosine here, this guy also moves to the baseband, right? So if that guy moves to the baseband, now that guy shows up like this. And also this guy moved to the right. So we also have a 2FC component like this one. Also minus 2FC, same as this guy. So we're going to have this spectrum at the receiver. Of course, at the receiver, after you multiply cosine, you're going to go through the band pass, low pass filter. So by putting the low pass filter like this guy and this guy will be gone, right? So we don't worry about these high frequency component because this guy will be removed anyway by low pass filter. Because we always do that, right? In the coherent detector, COSTAS receiver, every receiver we are putting the low pass filter. So these guys are gone, no problem. But let's look at this guy. Since we have a little bit spectrum here and also a little bit spectrum here, when you multiply cosine carrier, this guy now moved to the left and that guy moved to right. Now we have an overlap, right? Now we have overlap. Is that a problem or not? This kind of overlap is a problem actually, right? But what they are trying to do is when you have overlap, let me draw a little bit more. This overlap, here this overlap. So when you have always overlap, these are pretty much added. This comes here, this comes from the right, you are adding together. So when you add these two overlap, now what do you get? You're going to get this. you're gonna get this, the original one. So that's the intention. You know what I'm saying? So some of them coming from this guy, some from the left, and when you add it all together, you're gonna get the perfect shape again. Okay? So that's the VSB. Okay? All right.